Both of these files hold the same table, 2 million rows, 50 columns. Your query asks for 2 columns. In the CSV, a reader has to walk 991 megabytes of text to find them. In Parquet, the chunks holding those 2 columns come to 4.4 megabytes, about 224 times fewer data bytes than the CSV, before the metadata the reader also has to read. Ask instead for all 50 columns, and it collapses to 1.4 times. So the question was never which format is faster. It is how much of the file your query reads. Look at what is physically in a CSV. 1 line per row, fields separated by commas, every value written as text, no index anywhere. If your query wants a field from the middle, there is no offset to jump to. You get there by reading everything in front of it. Subscribe if you want the mechanism rather than the rule of thumb. Because the thing everyone always says, that Parquet is smaller, is true here and is still the wrong explanation. Asking for 2 columns instead of all 50 took 435 milliseconds, against 557 milliseconds for the whole row. Now the same rows written as Parquet. Same table, different arrangement on disk. The file is cut into row groups, 20 of them here, 100,000 rows each. Inside a row group, the values of a single column sit together in a column chunk, with their own type, their own encoding, and their own byte range. At the end of the file there is a footer, and the footer records where every chunk begins and how long it is. That is the whole trick. Your reader does not search the file. It looks up an offset and reads a range. Your query asks for 2 columns out of the 50. The footer points the reader at the chunks it needs, and those requested chunks come to 4.4 megabytes. That is 1% of a 440 megabyte file, and never goes near the other 48 columns. On this machine, that query took 14 milliseconds, against 435 milliseconds for the CSV. Now compare each format against its own full scan. The Parquet query was under 4% of it. The CSV query was 78%. Both readers were told to skip columns. Only one could act on it. Now take that advantage away. Same files, same engine, but this time the query reads all 50 columns. Parquet came in at 399 milliseconds. The CSV took 557 milliseconds. That is 1.4 times, and nothing like the gap you just saw. Once your query needs every column, there is nothing left to skip, and what is being measured is decoding against parsing, not layout. So if your job is a full export, or a script that reads whole rows and writes them somewhere else, the format matters far less to your runtime than you have been told. There is a second cost hiding in that text file, and it is types. A latency of 900 is stored in the CSV as the characters 900. Something has to turn those characters into a number for every value your query uses. Parquet writes the type into the footer and stores the value as bytes that already are that type. And to keep this honest, I handed the CSV reader the full column schema, so type inference is not inside any number in this video. Your CSV can certainly have a schema. It just does not carry one inside itself. Now size, and this is the part that gets explained wrong. The CSV is 991 megabytes. Write the Parquet with its compression codec switched off entirely, and it is 630 megabytes. The text file is about 1.5 times the size of that, with no compression codec applied to either file. What you are seeing there is binary values instead of characters, plus encodings like dictionary and run length, not a block compression codec. Then switch a strong codec on, and the Parquet lands at 328 megabytes. Now gzip the CSV, 328 megabytes. The zip text file is slightly smaller. So why not ship that? Because of what it takes to read it. A plain gzip stream has to be decompressed from the start. You cannot jump into the middle and pull out 2 columns, because the bytes before them are what decode the bytes after them. Parquet compresses the pages inside each column chunk independently of the other chunks, and the footer still records where those chunks sit. Same size on this data, different access. Compression shrinks a file. Layout decides what you can read out of it. Now filters, which is where the overclaiming starts. Parquet column chunks can carry statistics in the footer, the smallest and largest value inside each one. These files do, because I wrote them with statistics switched on. When your filter falls outside that range, the reader can skip that chunk without decoding it. So, a controlled test. The same 40 values are written twice. once with equal values together, once shuffled across the file. A filter on either one matches exactly 50,000 rows. On the clustered column, the reader touches one row group out of 20 and 183 kilobytes. On the shuffled column, it reads all 20 row groups and 5.2 megabytes. Same file, same predicate shape, 50,000 rows matched either way, and 28 times the bytes. So keep the two mechanisms apart. Reading only the columns you asked for is a property of the layout. It does not care how rows are ordered. Skipping row groups is conditional. It needs statistics in the file, a filter they can rule out, and data arranged so the ranges do not all overlap. And the shuffled filter still beat the text scan because projection still worked. One mechanism failed. The other did not. How much can be skipped is not a property of Parquet. It is a setting whoever wrote your file chose. I wrote this table 3 ways. One row group for all 2 million rows gives the smallest file, 340 megabytes. The encodings get more to work with. But the filter then scans 2 million rows to find 50,000 rows. Go the other way, 100 groups of 20,000 rows, and the reader scans 60,000 rows instead of 100,000 rows. But the file grows to 477 megabytes, and the filter took 3 times the time. Here is where that projection argument gets much weaker. The same 2 million rows, written with 6 columns instead of 50. The rows did not change. The width of the table did. Those 2 columns you wanted are now 11% of the Parquet file rather than 1%. You cannot skip what is not there. On a narrow table, the projection advantage shrinks sharply, so what matters much more is how wide your table is and how much of that width you actually touch. The format still does plenty, but it has far less room to skip. 2 shapes to make this concrete. First, a table you write once and query all day, 40 or 50 columns wide, where every dashboard on top of it selects 5 or 6 of them. That is the case this layout was built for, and the win is not a smaller file. It is that the column chunks nobody asked for are never read. Second, an export a colleague opens in a spreadsheet or a file you hand to a system you do not own. Nothing is scanned repeatedly and nothing is projected, so the analytical scan advantage may no longer be what decides the format. So when is the text file the right answer? When something on the other end has to read it and you do not control what it is. When the data is small enough that none of this matters. When a person has to open it and look. When you hand it over once and never scan it again. And when the tool receiving it does not handle Parquet well, which is still true more often than the internet admits. None of those are compromises. They are cases where interoperability is worth more to you than scan efficiency. In picking text, there is a correct decision. So the rule, and it is a set of questions rather than a threshold. Are you scanning this dataset over and over, or reading it once? Do your queries take a few columns, or all of them? Is your table wide or narrow? Are the types stable enough to be worth writing down? Does the thing on the other side read Parquet properly? And is there a column you filter on that could be written in order so that the statistics can actually rule something out? Answer those, and the format falls out on its own. Because what you are choosing is not a file extension. It is how much of the file your queries have to read.